Hello, this is Mr. Couple. This is PHYZR number 6, Acceleration Concepts. This is from the motion unit and it's page number 6. The purpose of this lesson is to address some misconceptions and just try to re-emphasize ideas about acceleration. Acceleration is one of the most confusing topics in high school physics, and so I really want to try to illustrate some of the more confusing aspects of acceleration with today's lesson. So make sure you pay attention. This is a must watch. We'll start with the boring stuff, the definition of acceleration. So acceleration, the symbol is lowercase a, and acceleration is the rate at which an object's velocity is changing. So in other words, since it's a rate, we can say it's basically the change in velocity an object experiences over a time interval. And so the formula is delta v over delta t. The change in velocity over the change in time. Now looking at this definition, we could ask, what are the units? So if we think, what are the units of velocity and what are the units of time? Well, the standard unit of velocity is meter per second. So we know that the unit of acceleration is going to be meters per second over seconds, the unit of time. Put that together and it's meter per second, meters per second per second. Or we can simplify it and just say meters per second squared. So that's the unit of acceleration, it's the meter per second squared. Now already you can see why acceleration is so confusing. Even the unit is confusing, that it has a square in it. And realize that the time is factoring into this unit twice. We get one unit of time from the velocity, which is the rate of change of position, and we get the other unit of time from the rate of change of velocity, the acceleration. So we have two rates. In fact, you can actually say acceleration is the speed of the speed. So you have two rates in here, which is why it's squared. That's the first thing that most students mix up, is that they think meters per second is the unit of acceleration. It's not. It's meters per second squared. This is really important. Don't mess this up. Look, most people, not just students, but just most people in general, make this mistake. They think that acceleration is how fast an object is moving. So they think, oh, like a Ferrari, that's like such a fast car, it has so much acceleration. And that's totally not what acceleration is. Acceleration isn't how fast an object is moving. That's not what acceleration is. Make sure you understand what acceleration really is. What acceleration is it's how fast the velocity of an object changes. It's not how fast the object is moving. It's not the velocity. Acceleration is how quickly the velocity changes. So you have to understand that acceleration has nothing to do with speed. It doesn't matter how fast an object is moving. It's only accelerating if the velocity changes. In fact, you can have an object that's at rest that's accelerating. This is such a confusing concept. Just all you have to do to make sure this makes sense is to just sever these two ideas right now in your head. Acceleration, velocity, they're not the same thing. Separate them out from each other. Don't make that mistake. Remember velocity? How fast the velocity of an object changes is acceleration. Velocity of speed and direction. So what that means is that an object is accelerating if either the speed or the direction is changing. So there are two ways that acceleration can manifest. So you can see an object is accelerating if it's changing speeds, and you can also see if it's accelerating if it's changing directions or if it's turning. So please understand that just because an object is moving, that doesn't mean it's accelerating. In order to be accelerating, it has to be getting faster, getting slower, or making a turn or changing direction. Okay, let's practice this a little bit. So I'm going to show you guys 3 videos, and for each video I want to know, is this car accelerating? So you're going to think to yourself while the video plays, is the car accelerating? What evidence do you see in the video? And make sure that you justify your answer. So here's the first video. What do you think? Was the car accelerating? Think about it some more. I'll give you about 10 seconds. Remember that acceleration is a change in speed or a change in direction. In this video, the speedometer here clearly shows that the object was not changing speeds. In fact, the object was at its max speed. It was topped out. In addition, the highway the car was driving down was a straight highway, no curves, no opportunity to change direction. So a car moving at constant speed in a straight line is not accelerating. There's no change in speed, there's no change in direction. Uniform motion, constant velocity, is zero acceleration. There's no acceleration unless you change speed or change direction. This car was not accelerating. See, even though the car was going 200 miles an hour, extremely fast, top speed, the fastest possible speed this car can go at, it was not accelerating because the speed and the direction were not changing. The velocity was constant. Let's move on to the next video. Is this car accelerating? So what do you think? Was it accelerating? Remember to justify your answer and provide evidence that supports your answer. Remember, to say whether there's acceleration or not, we need to know whether the speed or the direction is changing. In this video of the speedometer of a car, we can clearly see that the speed is changing. In fact, we watched the speedometer go from 0 all the way up to 140 miles per hour. Obviously, this car is accelerating because the speed is changing. So a car that experiences a change in speed is accelerating. And this is true whether the car speeds up or slows down. In both cases, the speed is changing, and that's enough to conclude that there's acceleration. Even though we didn't see outside the car to tell if the direction was changing, it didn't matter, because all that has to happen for acceleration to definitely be happening is the speed must change. If the speed were constant, then we'd need to look outside the car to see if the direction was changing. But in this case, we didn't need to. The speedometer was all we needed. So when the speed changes, acceleration is happening. Let's move on to the next video. Is this car accelerating? What do you think? Was the car accelerating? Remember to justify your answer. So what was different about this video compared to the other two videos? Did you notice? We couldn't see the speedometer in this video. We have no idea how the speed of this car is changing. In fact, we don't even know if it was changing. This car could have been going at constant speed. So can we answer this question? Can we say whether the car was accelerating or not? Of course we can, because a turning car is accelerating since the direction is changing. It didn't matter if it was going at constant speed. It didn't matter that we didn't know the speed. We definitely knew the car was turning. It has to have been accelerating. So if the direction changes, acceleration is happening. Alright, let's do a little wrap up here, a little review. So, which controls in a car cause the car to accelerate? I want you to think about that for a moment. Which controls in the car cause the car to accelerate? Most people are able to say the gas pedal, because when you step on the gas, the car increases its speed. Likewise, the brake pedal. When you step on the brake pedal, it decreases the speed of the car. But remember that acceleration also happens when direction changes, which means there's another control in this car, the steering wheel, which changes the direction. So all three of these controls can cause the car to accelerate. Many people think it's just the gas pedal, but actually no, anything that would cause the car to change speeds or change direction will accelerate the car. So isn't it kind of funny that we call the gas pedal the accelerator? Because we could use the same term for the steering wheel or the brake pedal. They're all accelerators. Let's talk about what it means when we say the direction of acceleration. Now remember, if the direction of the velocity is positive, that means the object's moving to the east. And if the direction of velocity is negative, that means the object's moving to the west. But acceleration is not the direction an object is moving. An object that has positive acceleration is not moving to the east. What's happening is that the velocity is changing to the east. Which means if the car was moving left to the west, then the velocity would change east, which means it would slow down. Or if the car was moving east and we change the velocity that same direction, then the car would get faster. So positive acceleration doesn't mean the car is speeding up or slowing down. It just means that the velocity is changing in the positive direction, that there's some force that is accelerating the object in the positive direction. Likewise, negative acceleration means the velocity is changing to the west. So there's something that's causing the object to accelerate in the western direction. Please don't confuse this. This is not the direction the object is moving, it's the direction of velocity is changing. Acceleration doesn't tell us how an object moves, it tells us how the velocity of the object changes. This is a very confusing idea, so we're going to do a few checks to make sure you understand it. Okay, here's our first example. Let's say that a car is moving to the east and the driver steps on the gas. So there goes the car moving to the east and gas. Now what was the direction of the velocity? You could see the car was moving to the right. So that's positive velocity. But what about the acceleration? What's the direction of the acceleration? We see that the car was already moving to the right, and stepping on the gas gives an additional boost to the right, which means the car is getting faster, which means the acceleration is in the same direction as the velocity. So in this case, stepping on the gas increased the velocity of the car, which means that the acceleration and velocity point the same way. Let's do another one. A car is moving east and the driver steps on the brakes. The direction of velocity? Still forward. It was to the right. That's positive velocity. This car never went backwards. It was always traveling forward. But what was the direction of the acceleration? Car is moving east and we brake. You can see that the velocity decreased, which means the acceleration must have been negative to oppose the velocity. So in this case, even though the car is traveling to the right, it's accelerating to the left. And this is kind of confusing that a car can be accelerating the opposite direction that it's moving. But realize that when this happens, it just means that the object slows down. That's all. Let's look at another example. A car moves west and the driver steps on the brakes. See, that entire time the car was moving to the left. That's negative velocity. But what direction was the acceleration? Car moves left and brakes. We see that the car was slowing down, which means the acceleration must oppose the velocity. So in this case, the car slowing down is an example of a positive acceleration. Now, this might be confusing at first because a lot of people think that positive acceleration means to get faster, but that is not what positive acceleration means. Just look at this picture for a second. In this case, the acceleration was positive because the car was slowing down. And when the car is slowing down, the acceleration and the velocity oppose each other. The car was moving left, and the acceleration changed that speed to the right, which made the car slow down. So one more example, when a car moves west and the driver steps on the gas. So the car was moving to the left, that's negative velocity. But what was the direction of the acceleration? cars moving left, and gases. We see the velocity is changing. In fact, the velocity is changing to the left because it's getting faster. So that's a negative acceleration. Here you can see negative acceleration doesn't mean slow down, because here's an example where an object actually speeds up from a negative acceleration. So let's try to summarize all this information. We notice that when the velocity and acceleration were both pointing the same direction, the object sped up. So when velocity and acceleration are parallel, the object gets faster, the speed increases. And when the velocity and acceleration oppose each other, when they point in opposite directions, the object slows down. This is a really easy way to think about it. It's going to avoid any confusion that you might have. I highly recommend that you write this down in your notes. So once again, if the velocity and acceleration are in the same direction, the object will get faster. And if the velocity and acceleration are in the opposite direction, it gets slower. So you can't just look at the sign of the acceleration, positive or negative, to tell you if the object's speeding up. You also have to look at the velocity. You need to know what direction is the object moving, what direction is accelerating, then you can decide if it's getting faster or if it's getting slower. Let's talk about gravity. So all falling bodies, if we ignore air resistance, they all fall with acceleration equal to 10 meters per second squared. Now this is an approximation, it's actually 9.8, but just to make the math easier, we're going to say 10 meters per second squared. And the direction of acceleration of gravity is always downward, because the Earth is pulling objects down towards it due to its gravitational attraction. And this is called the law of falling bodies. It was discovered by Galileo. All falling bodies fall with acceleration equal to 10 meters per second squared downward. This is a constant acceleration. Now please realize that this is only true if we're really close to the surface of the Earth and if we ignore air resistance, because we don't want gravity to get weakened by going out far away from the Earth. So we're going to stay close to the surface and we're going to ignore the effects of air resistance. So I want to take a closer look at the acceleration of gravity. So we'll say g. Little g will mean the acceleration of gravity. And so the acceleration of gravity is negative 10 meters per second squared. And the negative is because gravity, the acceleration of gravity, points downward. So here's a question. Let's say that an object is dropped from rest. You just let it go, just like in this picture. How much time will it take for the object to reach a speed of 20 meters per second? So I want you to think about that, and we'll get back to it in a moment. It's probably best if we make a table. So here's a table showing the various times, 0, 1, 2, 3, and 4 seconds, and we'll track the velocity. Now since the object was dropped, we know that its initial velocity was 0. And the acceleration of gravity says that every second the object will change its velocity by 10 meters per second downward. So after 1 second, the velocity will be negative 10. And after 2 seconds, it'll be negative 20. After 3 seconds, negative 30, and negative 40 after 4 seconds. The question was, an object is dropped, how much time will it take to reach a speed of 20 meters per second? So you can see here that it's 2 seconds for it to reach the speed of 20. Now remember, the negative in front of the 20 is simply the direction. That's what makes it velocity. Negative 20 is the velocity, but just 20 is the speed. So you can say the absolute value of this is the speed. So it took 2 seconds for the object to reach a speed of 20 meters per second. Gravity is a pretty quick acceleration. Let's look at the example of a baseball that's hit straight up into the air, and then gravity pulls it back down to the ground. When the baseball was rising up, the velocity was pointing up because the ball was rising upward. But it was a falling object, and all falling objects, when they're in free fall, when they're in the air, gravity is what accelerates them. So the acceleration of the ball is downward. Now this makes perfect sense. Think about it. If the velocity and the acceleration are pointing in opposite directions, what's going to happen to the speed of the baseball when it rises? It slows down. And when the baseball falls, what's the direction of the velocity and the acceleration? Well, the velocity is going down because it's falling, The acceleration is still from gravity, so it's still going to be pointing down. So what happens when both the velocity and acceleration are pointing downward? The ball speeds up. So it's slowing down, and now it's speeding up. I'd like to animate this with arrows. So the blue arrow is going to be the speed, the velocity, and the orange arrow is going to be the acceleration. Now the acceleration is going to be constant downward acceleration, but the velocity is going to change. And you see right at the top there's a moment of rest. So at the top, the ball temporarily comes to rest because that's the point where that upward velocity switches to pointing downward. And that's because the entire time the object was in the air, it was accelerating downward. So that constant downward acceleration is present even when the object is at rest. An object at rest can be accelerating as long as it's changing the velocity. And at that point, at the tippy top, the highest point that it reaches, it was still accelerating downward even though it was at rest, because that downward acceleration was changing the direction the ball was traveling. That was a turning point. So the acceleration is a constant 10 meters per second downward, just like the law of falling bodies said. There's no contradiction here. It's weird to think that an object can be moving up, that a baseball can be rising upward and accelerating downward, but that's because it's slowing down. It makes perfect sense to say that acceleration is constantly 10 meters per second squared downward. Let's put some numbers to this to make sure you really understand it. So let's say the baseball's hit straight up at a speed of 30 meters per second. My question is, how much time will it take the ball to reach its highest point? Think about it, see if you can figure it out. Like the previous question, let's make a table. So we know now at time 0, that's the initial velocity, and that was 30 meters per second upward. And we'll make that positive to signify that it was moving upward. The acceleration of gravity is -10, or 10 meters per second squared downward, which means every second that passes, the velocity is going to change by 10 meters per second downward. So if we're moving up at 30 and we change down by 10, then we'll be at 20. And another second passes, it'll be another change of 10 downward, and then we'll be at 10 meters per second squared. After 3 seconds, we'll be at 0 meters per second, and then finally after 4 seconds, we'll be at -10. And so now you can see that the ball has started to come back down again. So where was the highest point? It was when the velocity was 0, because at the highest point, that's the turning point, when it changes directions, when it goes from rising to falling. That's its highest point, and that's 3 seconds later. So at the highest point, the speed is, and the acceleration is. I want you to fill in those blanks now. Make sure you understand this. At the highest point, what's the speed? Put it in this blank. And what is the acceleration at that point? So in other words, what I'm asking you is, what's the speed at the highest point? And what's the acceleration at the highest point? Well, obviously the speed is 0. At the highest point, we just said that. So if the speed is 0, what's the acceleration? This is the highest point that the ball rises to. The acceleration is -10 meters per second squared. Did you think it was 0? It's not 0, because remember, at the highest point, the baseball's turning around. It's at a turning point. It's only at rest for a moment. It doesn't stay at rest. It's turning around. It's changing directions. This object was constantly accelerating at -10. The entire time the baseball is in the air, no matter which direction it's moving, or if it's even moving at all, it's constantly accelerating at 10 meters per second squared downward. So that's it for this PHYZR. I hope you have a wonderful day. This has been Mr. Keppel. I'll see you in class.